Your morning coffee is governed by the same rules as particles inside the sun. Quantum physics is not a distant abstraction, but the hidden architect of your daily life, from the phone in your hand to the thoughts in your mind. This journey will reveal 38 astonishing ways the quantum realm shapes your reality, leaving you with a completely new way of seeing the world. We will uncover how a simple decision can mirror a particle in two places at once, and why the security of your bank account depends on spooky connections across space. What is the most surprising quantum link you expect to find in your own life? You stand before your closet, a familiar morning paralysis setting in, the blue shirt or the gray one. For a few moments, both options exist with equal weight in your mind. This is a human experience of superposition. In the quantum realm, a particle like an electron does not choose a single location or state until it is measured. It exists in a haze of all possible positions, a probability cloud described by its wave function. Your undecided mind, holding both the blue shirt and the gray shirt as real possibilities, mirrors this fundamental quantum reality. As one physicist noted, the moment you finally reach for one hanger, your choice collapses the possibilities into a single, definite reality. This is strikingly similar to the wave function collapse in a quantum system. Some researchers even propose that the brain's decision-making machinery may operate on quantum-like principles, weighing probabilities in a delicate superposition before committing to an action. How many times today have you existed in that blurred state of being, not yet decided, all options still on the table? This intimate connection suggests that the quantum world is not separate from our inner world of choice and consciousness, a mystery that pulls us deeper into the fabric of reality itself. That moment of decision, collapsing the possibilities into a single reality, is mirrored by the very device you might use to document your choice. Your smartphone, a pocket-sized marvel, operates on a principle that seems to defy common sense. Think about a weak Wi-Fi signal, the kind that shows only one bar, yet a message still manages to arrive. It feels like a minor miracle, a digital Houdini act. This everyday frustration is a perfect gateway to one of quantum physics' most bizarre feats, quantum tunneling. In the classical world we experience, if you throw a ball at a wall, it bounces back. It simply does not have the energy to pass through. But in the quantum realm, particles like electrons play by different rules. An electron faced with an insulating barrier, a wall it seemingly cannot climb over, has a finite chance of just appearing on the other side. It does not go over the top, it tunnels through. This is possible because an electron is not a tiny, solid ball. It is better described as a smeared-out probability cloud, a set of potential locations, and that cloud has a tiny, non-zero value even inside and beyond a barrier. This quantum magic is not just a laboratory curiosity. It is the bedrock of modern technology. The transistors in your phone's processor are so incredibly small that engineers deliberately harness electron tunneling to make them work. As one semiconductor engineer put it, we are not just building around quantum effects anymore. We are actively designing them into the heart of every chip. We have engineered a paradox into billions of devices, relying on particles to be where they logically should not be, just to make your phone fast and efficient. This technological marvel, humming quietly in your pocket, is a direct line to the strange, probabilistic heart of the universe. And if quantum rules can orchestrate the global dance of information, what other intimate, invisible processes do they govern within us? That inexplicable knowing between two people echoes one of the most profound mysteries in all of science. For close twins or lifelong friends, a sudden thought or feeling can cross a continent in an instant, a silent understanding that defies simple explanation. This deep, non-local bond finds a startling parallel in the quantum phenomenon known as entanglement. Albert Einstein famously dismissed it as spooky action at a distance, baffled by its implications. When two particles become entangled, they form a single, unified quantum system. Measuring one particle, perhaps finding its spin pointing up, will instantly force its partner, no matter how far away, into a corresponding state, spin down. This connection is immediate, transcending the speed of light and the vast emptiness of space between them. While no one is suggesting that human brains share a literal, physical entanglement, the analogy is powerful and thought-provoking. The deep, intuitive connections we feel with those we are closest to mirror this quantum weirdness in a poetic, almost metaphysical way. Some researchers in quantum biology even speculate that the very substrate of consciousness, the intricate workings of our neural networks, might leverage subtle quantum processes to achieve its remarkable capabilities. This is not to reduce human connection to mere physics, but to wonder if the universe's fundamental principle of interconnectedness manifests on every level, from the subatomic to the social. Can you recall a moment when you felt a sudden, inexplicable pull to call a loved one, only to find they were thinking of you at that very same instant? That profound sense of a bond that distance cannot sever hints at a universe far more deeply woven together than we ever suspected. A social fabric that might, in its most intimate threads, be stitched with quantum principles. That same photo you just posted, a moment of celebration shared with the world, creates a ripple of digital uncertainty the moment it leaves your phone. You want the likes and comments, the positive social momentum, but you also want to maintain control over your personal space. This modern dilemma is a startling reflection of a cornerstone of quantum theory, Heisenberg's uncertainty principle. In the subatomic world, this principle asserts a fundamental limit to knowledge. You cannot simultaneously know both the exact position and the exact momentum of a particle like an electron. The more precisely you pin down its location, the more its speed and direction become a blurry unknown, and vice versa. Your online life operates under a strikingly similar rule. The more you reveal about your precise location, tagging yourself at a specific restaurant or on a particular beach, the less certain you become about your social momentum. Who has seen this data? How will it be used? What future interactions might it trigger that you cannot foresee? As one data privacy expert noted, every photo you share is wrapped in a cloud of metadata, a digital wave function of information that includes the when, where, and how of its creation. The act of posting it is the measurement, collapsing that cloud of possibilities into a single, public reality, but one whose consequences for your privacy remain fundamentally uncertain. This digital uncertainty principle is a powerful reminder that observation always changes the system. By putting a part of your life under the spotlight of social observation, you irrevocably alter its trajectory, trading a measure of privacy for a measure of connection in a delicate, quantum-like balance. The passwords protecting your digital life and the shuffled playlist that surprises you are both rooted in a cosmic lottery. True, unpredictable randomness is surprisingly difficult to generate in a deterministic computer system. Most software random number generators are merely pseudorandom, following complex but ultimately predictable algorithms. For the absolute chaos required for top-tier encryption or a genuinely random song shuffle, engineers must look beyond our classical world, directly into the seething quantum vacuum. Empty space, it turns out, is not empty at all. It is a vibrant sea of energy, constantly bubbling with quantum fluctuations. In a fleeting, spontaneous dance, pairs of virtual particles and antiparticles pop into existence for an unimaginably short moment before annihilating each other and vanishing. This perpetual, unpredictable froth is the ultimate source of cosmic static. Hardware random number generators tap directly into this quantum noise, using it to produce a stream of numbers that are fundamentally and profoundly random. A sensor might measure the exact time a radioactive atom decays, an event governed by pure quantum probability, or detect the random noise generated by these vacuum fluctuations. This raw quantum uncertainty is then converted into the digital keys that secure your bank transactions and the shuffle that delivers your next unexpected song. Your financial security, in a very real sense, is guaranteed by the restless, indeterminate energy of the universe. This means the very fabric of reality, with its inherent randomness, is woven directly into the architecture of our digital world. How many other cosmic processes are silently operating within the devices we take for granted, their quantum hearts beating just beneath the sleek, glass surface? The very reality you perceive shifts with the simple act of paying attention. You are a single, continuous entity, yet you are perceived, and you perceive yourself in profoundly different ways. At home, you are a parent, a source of comfort and guidance. In the office, you are a leader, a strategist making decisive calls. You are not two different people, but one being whose dominant traits are called forth by the context of observation. This human experience is a powerful echo of one of quantum physics' most baffling revelations, wave-particle duality. For centuries, scientists debated whether light was a wave, like ripples on a pond, or a stream of tiny particles. The stunning answer, confirmed through countless experiments, is that it is both. How light behaves depends entirely on how we choose to measure it. Set up an experiment to detect a wave, and it will show interference patterns, crests and troughs overlapping. Set up an experiment to detect a particle, and it will strike a detector as a single, localized photon. Its very nature is contextual, a fluid potential that crystallizes into a specific form upon interaction. This is not just true for light, but for all matter, including the electrons that make up your body. A sound in your daily life mirrors this perfectly. With your eyes closed, a siren is an immersive wave of vibration, a field of auditory energy filling the air. The moment you turn to look, you locate its source, a specific particle-like object, an ambulance speeding down the street. The reality of the siren did not change, but your mode of perception collapsed its possibilities into a single, definite experience. This quantum principle fundamentally challenges the classical idea of a single, objective reality sitting out there, independent of us. It suggests that reality is, in a sense, a dialogue, a relationship between the observer and the observed. The universe presents different faces depending on the questions we ask of it. If something as fundamental as light refuses to be pinned down to a single identity, what does that imply about the solid, stable world we feel we inhabit? This profound mystery invites us to question not just the nature of light, but the very nature of our own participation in crafting the reality we see. The universe seems to conspire to keep a watched pot from boiling. You stare, anticipation building, yet the water remains stubbornly still. The moment you turn your attention elsewhere, a triumphant roar erupts from the stove. This everyday frustration is an uncanny echo of a quantum phenomenon known as the Zeno effect. In the subatomic world, an unstable particle, poised on the edge of decay, can be held in a state of suspended animation simply by measuring it repeatedly. The act of observation resets its internal quantum clock, freezing it in its initial state. It is as if the universe, under intense scrutiny, becomes self-conscious and hesitates to change. This principle translates with startling clarity to the realm of human performance. A musician, hyper-focused on not missing a single note, can find their fingers freezing on the keys. A public speaker, mentally chanting "Do not stumble," often trips over their own words. The very intensity of your observation, your focused intent on preventing a mistake, can lock your system into the state you are trying to avoid. Your mind, in its own way, is performing a continuous measurement, collapsing the fluid possibilities of a flawless performance into the rigid reality of a feared error. This reveals a profound truth about the power of attention. Our focus is not a passive spotlight. It is an active force that shapes outcomes, from the decay of an atom to the flow of a creative idea. What if the key to unlocking your potential is not in watching the pot, but in trusting the water to boil on its own? A gecko defies gravity, its tiny feet clinging to polished glass without a single slip. This everyday miracle of biology is powered by an invisible quantum handshake. Between any two surfaces brought incredibly close together, a mysterious force emerges, pulling them together. This is the Casimir effect, a phenomenon predicted by quantum theory. Empty space is not truly empty but filled with a seething sea of virtual particles that constantly wink in and out of existence. When two plates are placed almost touching in a vacuum, they limit the kinds of quantum fluctuations that can form in the gap between them. More fluctuations occur on the outer sides of the plates, and this imbalance of quantum pressure pushes the plates together. It is a force born from the restless energy of nothingness itself. The gecko's foot is a biological masterpiece evolved to harness a version of this very force. Its toes are covered in millions of microscopic hairs, each one splitting into hundreds of even smaller bristles. This creates an enormous surface area that can get so close to the molecular ridges of a wall that van der Waals forces kick in. These are the same type of weak electrical attractions that are the macroscopic cousins of the Casimir effect, a quantum grip operating at a molecular scale. The gecko does not use glue or suction. It is quite literally holding on to the wall with the ephemeral push and pull of the quantum world. This is a stunning example of nature, through billions of years of evolution, engineering a solution that leverages the strange rules of quantum mechanics. Life is not just existing alongside these principles, it is actively using them. If a simple lizard can scale a wall using quantum forces, what other biological marvels are operating just beneath the surface of our perception? Their secrets written in the subtle language of the very small. That silent, shared understanding in a packed elevator, where gazes drift to the floor, numbers and bodies hold a rigid stillness, is a social contract written in quantum code. This deep-seated need for a personal bubble mirrors one of the most fundamental laws governing matter itself, the Pauli exclusion principle. In the quantum world, this principle dictates that two identical particles known as fermions, electrons being the most famous example, cannot occupy the exact same quantum state. They are forbidden from having the same energy, the same spin, the same location. It is this cosmic rule of personal space for particles that prevents all the electrons in an atom from collapsing into the same low-energy orbit. Instead, they stack into orderly shells, creating the diverse chemical elements and the very structure of the world you can touch. Your instinctive recoil in a crowded space is a macroscopic echo of this subatomic law. You are unconsciously resisting occupying the same social and physical state as the person next to you. You cannot both be the one initiating conversation while also being the one avoiding it. You cannot both claim the same square of floor as your sole domain. So you settle into different social states, one person studying their phone, another staring at the ceiling, a third counting the seconds until the doors open. This quantum principle, etched into the behavior of the electrons that build your body, seems to also be encoded in your most basic social instincts. It is the invisible force that orchestrates the delicate dance in a crowded room, ensuring we maintain our individual orbits even when our physical shells are forced into proximity. How many of our unspoken social rules, the subtle negotiations of space and attention, are guided by these ancient, fundamental laws of the universe? This suggests that the architecture of an atom and the etiquette of a subway car might be distant branches of the same deep, cosmic root. The same quantum principle that orchestrates your personal space also guides the most advanced tools of modern medicine. Inside the cavernous core of an MRI machine, A silent, invisible drama unfolds, one governed by a fundamental property of the quantum world known as spin. Every atomic nucleus, like the countless hydrogen atoms in the water molecules of your body, possesses this intrinsic angular momentum. It is not that these particles are literally spinning like tiny tops, but they do carry a magnetic orientation, a sort of innate compass needle. When you lie within the powerful magnetic field of the scanner, a vast majority of these nuclear spins are coaxed into alignment, much like iron filings organizing themselves around a magnet. This orderly state is then gently disrupted by a pulse of radio waves. As the nuclei relax back into their aligned positions, they release their own faint radio signals, each one a unique echo of their quantum environment. These signals are not random noise, they are a detailed symphony of data. A sophisticated computer listens to this quantum chorus, translating the subtle differences in how fat, water, and tissue release their energy into a breathtakingly precise, three-dimensional map of your internal landscape. That last medical scan, revealing a torn ligament or a healthy brain, was not just a medical procedure. It was a direct conversation with the quantum spin of your own atoms. We have learned to ask questions of the subatomic world and interpret its answers to heal the human body. This profound link forces a remarkable realization. The most intimate view inside ourselves is painted with the brush of quantum mechanics. What other hidden dialogues between our bodies and the quantum realm are waiting to be heard, offering new ways to see, to diagnose, and to cure? Your phone lights up with a notification, a single icon holding a universe of possibility. You see the sender's name, but the content remains a sealed box. And in that moment before you tap, the message exists in a perfect, agonizing superposition. It is both wonderful news and terrible news, a job offer and a rejection, a cheerful hello and a difficult goodbye. This digital limbo is a direct parallel to one of quantum physics' most famous thought experiments, Schrödinger's cat. In that hypothetical scenario, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers and the poison is released. Since the atom's decay is a quantum event governed by probability, the cat is considered to be both alive and dead simultaneously until someone opens the box to look. The act of observation collapses the wave function, forcing a single reality into existence. Your unread message is your own personal Schrödinger's box. The moment you choose to observe it, to open the app, you collapse that cloud of potential outcomes into a single, definite, and often emotionally charged reality. The superposition is destroyed, replaced by the hard truth of the text on the screen. This is more than just a clever metaphor. It reveals how quantum principles provide a powerful framework for understanding the very nature of information in our lives. Information itself can exist in a state of potential, its meaning and impact unresolved until it interacts with a conscious mind. How much of our daily anxiety is rooted in these uncollapsed possibilities, the boxes we are afraid to open? This quantum lens reframes our relationship with the unknown, suggesting that uncertainty is not a flaw in the system, but a fundamental property of a universe built on probability, a property that echoes from the atom all the way to the ping of your phone. That unread message holds a universe of possible outcomes, but the very energy your phone uses to display it connects to a quantum process even more fundamental. A sunlit leaf is a master of energy conversion, and its secret weapon is a quantum trick called coherence. For decades, biologists assumed that the energy from a captured sunlight particle, a photon, would bounce randomly through the molecular forest of the leaf until it reached the reaction center where it is put to work. This random walk would be slow and inefficient, but nature, it turns out, is far more clever. The energy does not take a single path. In a state of quantum coherence, it behaves like a wave, exploring all possible pathways through the photosynthetic complex at the very same time. It is as if the energy is testing every route in an instant, instantly finding the quickest and most efficient path to its destination. This is not a slow, stumbling search. It is a coordinated, wave-like exploration that happens in femtosecons, millionths of a billionth of a second. This quantum advantage makes the process astonishingly efficient, approaching 100% in ideal conditions. Your salad, the oxygen in your lungs, the very foundation of the food chain, is supercharged by quantum mechanics. This is quantum biology, not in a lab, but in the tree outside your window. The green world around us is not just living, it is leveraging the bizarre rules of the quantum realm to sustain life itself. This forces a profound shift in perspective. The boundary between the inanimate quantum world and the living, breathing world of biology is far more porous than we ever imagined. If a simple plant can harness quantum weirdness to feed the planet, what other biological processes, perhaps even within our own bodies, are relying on these hidden quantum advantages to function? The security of your online bank account is guarded by a silent sentinel that cannot be bribed or fooled. The fundamental laws of quantum physics themselves. This protection comes from a remarkable technology known as quantum key distribution. Imagine a digital conversation where the very act of a spy trying to listen in creates an unavoidable disturbance, instantly revealing their presence. This is the genius of QKD. It works by sending the key needed to encrypt your financial data, not as a stream of ones and zeros, but encoded into individual photons, the fundamental particles of light. These photons are prepared in specific quantum states, a delicate and fragile condition. Now, here is the unbreakable rule of the quantum world. Any attempt to measure such a system will inevitably alter its state. An eavesdropper trying to intercept one of these photons to read the key will, without fail, change its quantum signature. The legitimate sender and receiver on either end of the line will immediately detect this disturbance in the transmission. They will know with absolute certainty that the line has been tapped, and they will simply discard that compromised key and generate a new one. Your sensitive information is never sent over this quantum channel, only the key to unlock it, and that key is protected by a law of nature. This is not a mathematical puzzle that can be cracked with a faster computer. It is a physical impossibility. Your financial privacy in that moment of checking your balance is secured by the profound quantum principle that observation is an interaction, a force that always leaves a mark. This transforms our digital world from a place of fragile digital locks into a fortress whose walls are made of the very fabric of reality. The same quantum rules that secure your bank account also orchestrate a silent, gravity-defying ballet inside specialized laboratories. Picture liquid helium, cooled to a few degrees above absolute zero, spontaneously flowing up the sides of its container and over the rim, as if it has decided to ignore gravity entirely. This is a superfluid, a state of matter where friction vanishes and flow becomes perpetual. Its behavior stems from a quantum phenomenon known as Bose-Einstein condensation. When certain types of particles, called bosons, are cooled to near absolute zero, they lose their individual identities. They all collapse into the same, lowest possible quantum state, becoming a single, giant quantum wave. This unified entity, a Bose-Einstein condensate, behaves as one coherent superatom. The individual particles are no longer bouncing around independently. They are marching in perfect, collective lockstep. This collective unity is what allows the superfluid to climb walls. It is one single quantum object responding to subtle forces like the attraction between the liquid and its container, forces that normally cannot overcome gravity and friction. While creating a pure BC requires incredibly sophisticated lab conditions, the principles are vividly displayed in the eerie flow of superfluid helium. This is not just a laboratory curiosity, It is a quantum state with profound utility. Superfluid helium is used to cool the superconducting magnets in MRI machines, and the exquisite sensitivity of Bose-Einstein condensates themselves is being harnessed to build quantum sensors of unimaginable precision. These sensors can detect tiny shifts in gravity, potentially mapping underground resources, or measure time with such accuracy that they could reveal subtle changes in the fundamental constants of the universe. The bizarre behavior of a liquid crawling out of its beaker is a direct window into a quantum collective, a state where individuality dissolves into a unified whole, and that unity is now guiding us toward technologies that can measure the fabric of reality itself. The warmth of the sun on your skin is a gift from quantum uncertainty. Deep within the sun's core, a titanic struggle occurs every second. Protons, the nuclei of hydrogen atoms, all carry a positive electrical charge, and like identical poles of a magnet, they fiercely repel one another. The temperature and pressure in the core are immense, hurling these protons toward each other at fantastic speeds. But the electrical barrier between them, known as the Coulomb barrier, should be insurmountable. Classically, they could never get close enough to fuse and unleash the nuclear energy that powers a star. Their salvation is quantum tunneling. Each proton is not a definitive point, but a cloud of probability. There is a small, but non-zero, chance that a proton will not collide with the barrier, but will instead tunnel straight through it, appearing on the other side where the strong nuclear force can grab hold and forge a new element, releasing light and heat in the process. Without this quantum loophole, the sun and every other star would be dark, cold furnaces, unable to ignite. The light that allows you to see, the heat that warms the planet, the very energy that drives photosynthesis and sustains the entire food chain, all of it depends on particles being where they logically should not be. Your existence is literally fueled by a quantum miracle happening 93 million miles away. A constant reminder that the probabilistic rules of the very small are the architects of the very large. That sudden stumble in your step when you notice someone watching is a profound human echo of the quantum world. You were walking perfectly until the moment of observation, and then your own self-awareness disrupted the flow. This is the observer effect. Not in a lab, but in the theater of your own life. In quantum mechanics, measuring a particle's position requires interacting with it, often by bouncing a photon off it, which inevitably gives it a tiny kick, changing its momentum. The system is irrevocably altered by the very act of trying to see it. Your performance under pressure operates on a similar principle. When you are alone, playing a musical piece or practicing a speech, your actions flow from a state of unobserved potential. The moment an audience, or even your own critical inner voice, turns its attention to you, the system is measured. Your focus shifts from the fluid action to the fear of the outcome. This internal observation, this hyper-awareness of being watched, collapses your smooth performance into a conscious, hesitant series of motions. You are no longer simply performing, you are observing yourself perform, and that split in attention introduces a kind of psychological friction. The athlete chokes at the free throw line, the singer's voice wavers on the high note, not because they lost their skill, but because the act of observation, both external and internal, changed the state of the system. It reveals that our consciousness is not a passive witness but an active participant, capable of shaping reality through the simple, powerful, and often disruptive act of paying attention. The vibrant colors dancing across your television screen are not just a product of advanced engineering, but a direct manifestation of quantum confinement. Each pixel of pure, saturated color is generated by crystals so small they are measured in nanometers, structures known as quantum dots. These are not just tiny specks of semiconductor material, they are cages for electrons. In the macroscopic world, the color a material emits is determined by its chemical composition. But at the nanoscale, a new rule takes over. The size of the crystal itself dictates its properties. A larger quantum dot, with more room for its trapped electron to move, emits light toward the red end of the spectrum. A smaller dot, tightly confining the electron, forces it to emit a higher energy photon, which we see as a brilliant blue. By precisely controlling the size of these nanocrystals during manufacturing, engineers can tune the color they produce with extraordinary accuracy. Your QLED television uses a grid of these quantum dots, illuminated by a pure blue backlight, to create a palette of colors far more vivid and precise than traditional displays could ever achieve. The rich crimson of a superhero's cape and the deep emerald of a forest are literally painted with quantum mechanics. We have learned to sculpt matter at the atomic level, not for some esoteric laboratory experiment, but to enhance the stories we tell and the worlds we escape into. This seamless integration of quantum weirdness into our living rooms is a quiet revolution, a testament to our ability to harness the fundamental rules of the universe for pure aesthetic joy. The very act of watching a sunset in a film is now a dialogue with the quantum realm, where the size of a crystal dictates the beauty we perceive. The same quantum static that secures your bank account also dictates the ultimate fate of the cosmos. The void of space is not a true void, but a vibrant, seething sea of energy. Quantum field theory tells us that at the very smallest scales, empty space is a turbulent foam where pairs of virtual particles and antiparticles constantly pop into and out of existence, borrowing energy from the vacuum for a fleeting instant before vanishing. This perpetual, chaotic dance is not without consequence. It imbues every cubic centimeter of nothingness with a background energy, a pressure known as vacuum energy. This is not just a theoretical curiosity. It is a leading candidate for the most profound mystery in modern cosmology, dark energy. Astronomical observations have revealed that the expansion of our universe is not slowing down, as one might expect from the pull of gravity, but is instead accelerating at an ever-increasing rate. Something is pushing the galaxies apart, and the most straightforward explanation lies in this inherent energy of the vacuum. This vacuum energy manifests as a repulsive force, a kind of cosmic anti-gravity encoded into the fabric of spacetime itself, known as the cosmological constant. The fate of the entire universe, whether it will expand forever into a cold, dark emptiness or eventually reverse its course, hinges on the precise value of this quantum energy density. The largest structures we can observe, the vast cosmic web of galaxies stretching across billions of light years, are being sculpted by the restless activity of the quantum void. This means the grandest narrative of all, the story of the cosmos from its fiery birth to its distant future, is being written by the same unpredictable, effervescent quantum fluctuations that power the random number generator in your phone. The emptiness between the stars is not empty at all. It is the most active, dynamic player in the universe, and its quantum heartbeat is echoing across the expanse of space and time. That satellite-guided turn you just made onto a new street was orchestrated by a clock that never loses a second. The global positioning system is a technological marvel built on a foundation of quantum precision, all thanks to the atomic clocks aboard each satellite. These are not ordinary timepieces. They are devices that measure the unwavering rhythm of the atom itself. A cesium atom, when excited by microwave energy, vibrates at an exquisitely specific frequency, exactly 9,192,631,770 times per second. This quantum vibration is the most stable metronome we have ever discovered, and it defines the very length of a second. Each tick of these atomic clocks marks the passage of time with a fidelity that is almost incomprehensible. But this incredible accuracy would be useless without another piece of the puzzle, Einstein's theory of relativity. The satellites are moving at tremendous speeds relative to Earth, which causes their clocks to run slightly slower due to special relativity. At the same time, they are in a weaker gravitational field, which makes their clocks run faster according to general relativity. These tiny, counteracting effects must be calculated and corrected for in real time. If the satellite's software did not account for these relativistic shifts, the GPS would accumulate errors of over 6 miles in a single day. Your ability to find the nearest coffee shop or navigate a cross-country road trip depends on this delicate fusion of quantum mechanics and relativity, a symphony of the very small and the very fast playing out overhead. Every time you follow a blue dot on a map, you are trusting a network of quantum vibrations, perfectly synchronized and corrected for the warping of spacetime itself. This invisible guidance system is a constant reminder that our mastery of the universe's deepest laws is not confined to laboratories, but is woven directly into the fabric of our daily journeys, guiding us one precise turn at a time. Our very language is quietly absorbing the logic of the quantum world. You might describe a breakthrough in technology or a sudden personal transformation as a quantum leap, meaning a massive, discontinuous jump forward. This common phrase has a precise origin in atomic physics, where an electron orbiting a nucleus can only exist in specific, discrete energy levels. It cannot drift gradually from one level to another. It must vanish from one and instantly reappear in the other, making a quantum jump. This is not a small step, but a fundamental, all-or-nothing transition between allowed states. The fact that this term has escaped the laboratory and entered our daily lexicon is deeply significant. It shows that we are intuitively grasping for a new metaphor to describe change itself, one that is not slow and linear, but sudden, profound, and revolutionary. We are moving beyond the old, mechanical models of incremental progress and beginning to think in terms of probability clouds and state changes. When a company's stock price takes a quantum leap or an artist makes a quantum leap in their work, we are describing a shift that feels foundational, a reconfiguration of the very system. This is more than just borrowed jargon. It is evidence of a cultural osmosis, where the most successful scientific theories eventually reshape our conceptual frameworks. The way we talk about change is beginning to mirror the way the universe actually operates at its most fundamental level. If our language is already evolving to accommodate these quantum ideas, what other profound shifts in our collective thinking are just beginning to bubble up from the subatomic depths? The quantum revolution is not just about making our current electronics faster. It is about redesigning them from the inside out with materials that defy classical logic. Imagine a substance that acts as a perfect insulator in its core, blocking all electrical flow, yet its outer skin conducts electricity with zero resistance, as if coated in a perfect quantum lubricant. This is not science fiction. It is the reality of topological insulators, a new phase of matter whose existence was predicted by the mathematics of quantum geometry. The secret lies not in the material's chemistry, but in its shape, its topology in a quantum sense. Think of a donut and a coffee cup. To a topologist, they are the same object because one can be smoothly deformed into the other without cutting a new hole. A topological insulator has a similar, immutable quantum property, a kind of twist in its electronic wave function that cannot be undone by minor imperfections or distortions. This robust topological state forces electrons to travel in one direction only along the material's surface, immune to the defects and impurities that normally scatter electrons and cause energy loss in conventional wires. The implications for our future are staggering. These materials could form the backbone of ultra-efficient electronics, where electricity flows without wasteful heat, and of powerful quantum computers, where the protected surface states could be used to create stable quantum bits. The very geometry of the quantum world, a hidden landscape of shapes and twists in probability, is being mapped to build the next generation of technology. This means the future of your phone, your computer, and global communication networks will not be written in silicon alone. but in the profound and elegant language of quantum topology, a language where the shape of nothingness dictates the flow of everything. A bird's unerring flight across thousands of miles of featureless ocean is guided by a compass we cannot see, tuned to a field we cannot feel. This profound mystery of migration finds its most compelling explanation not in biology alone, but in the quantum realm. Scientists now believe that certain birds, like the European robin, possess a biological quantum sensor in their eyes, a mechanism known as the radical pair effect. It begins when light strikes a specific protein in the bird's retina, causing a molecule to donate an electron, creating a pair of molecules each with an unpaired electron. These two electrons become quantum entangled, their spins intimately linked. The orientation of Earth's weak magnetic field directly influences the quantum spin states of these entangled electrons. Depending on the field's angle, the electron pair will exist in either a singlet or a triplet state, which in turn triggers a different chemical signal in the bird's brain. It is as if the bird perceives the planet's magnetic field lines as a subtle visual pattern overlaid on its sight, a heads-up display painted by quantum entanglement. This is not a metaphor. It is a biochemical reaction driven by one of the most bizarre phenomena in physics. Nature, through billions of years of evolution, has engineered a living, breathing quantum navigation system. Long before we ever conceived of entanglement in our laboratories, birds were crossing continents using a sense built from spooky action at a distance. This forces a humbling realization that the line between the quantum world and the living world is not just blurred. It was never there to begin with. The same quantum laws that govern particles in a lab are actively sensing, guiding, and directing life all around us. What other ancient, instinctual knowledge is written in the silent language of spinning electrons? Einstein and his colleagues framed their famous paradox not as a celebration of quantum weirdness, but as a challenge to its very sanity. They argued that if quantum mechanics were a complete description of reality, then it implied a spooky, instantaneous connection between entangled particles, a notion that violated the sacred rule that nothing can travel faster than light. This EPR paradox was intended to show that the theory was flawed, that there must be some hidden, local variables guiding the particle's behavior. The stunning twist came decades later when experiments proved that the spooky action was real. Entangled particles do influence each other instantly, their fates intertwined across any distance, confirming the non-local nature of the universe that Einstein had so deeply resisted. This profound interconnectedness at the quantum level finds a powerful echo in the fabric of our modern global society. A political decision in one nation triggers an immediate economic tremor in markets across the globe. A viral social media post in one time zone can ignite a cultural firestorm in another within minutes. These are not slow, causal chains. They are near instantaneous correlations, a web of global entanglement where events are linked in ways that defy simple, linear cause and effect. Our classical intuition, which expects a clear and local sequence of events, struggles to comprehend this new reality, just as Einstein's intuition rebelled against quantum non-locality. The quantum world, with its baffling EPR correlations, provides a startlingly accurate framework for understanding our hyper-connected world, suggesting that we are all part of a deeply interwoven system where a change in one part resonates everywhere, instantly. The precise resistance of the wire in your phone charger is certified by a quantum dance that occurs at near absolute zero. This brings us to the 24th connection, where the very definition of an ohm, the unit of electrical resistance, is now anchored in the quantum world through the quantum Hall effect. When a thin sheet of semiconductor is cooled to a few degrees above absolute zero and subjected to a powerful magnetic field, something extraordinary happens to the flow of electrons. They are no longer free to move in any direction, but are forced into circular orbits at the material's edge. In this state, the material's electrical resistance does not change smoothly with the magnetic field. Instead, it jumps to a specific value and then plateaus, forming a perfect staircase of resistance. These plateaus are quantized, meaning they occur at exact fractions of a fundamental constant of nature. The resistance at these steps is so perfectly defined and reproducible that it is considered a universal standard. This means the tools used to calibrate every multimeter, every power grid sensor, and every piece of electronic test equipment in the world are ultimately tracing their accuracy back to this bizarre quantum behavior. The consistency of the device you are using right now to listen to this, its reliable performance, is underwritten by the unerring predictability of electrons marching in lockstep under a magnetic field. We have handed over the keys to our global electrical infrastructure to a quantum phenomenon, trusting its perfect steps to ensure that a volt in Tokyo is exactly the same as a volt in Toronto. How many other invisible, quantum standards are silently governing the reliability of our modern world, their constancy woven into the very pulse of our civilization? A sharp memory from childhood can feel as real as this moment, yet its edges soften with every passing year. The vibrant colors fade to pastels, and the crisp sounds become a muted echo. This gentle erosion of our past is a deeply human experience, and it finds a startling parallel in one of the most crucial processes in quantum physics, decoherence. In the pristine isolation of a lab, a quantum system can maintain its superposition, happily existing in multiple states at once. But the moment it interacts with its environment, bumping into even a single stray air molecule or a faint whisper of radiation, that delicate state of multiple possibilities collapses. The system is forced to choose a single classical reality. This loss of quantum coherence is decoherence, and it is the primary reason why we do not see quantum weirdness in our everyday macroscopic world. Everything is constantly interacting with everything else, drowning out the quantum symphony in a roar of classical noise. Your fading memory operates in a remarkably similar way. A new, vivid experience is like a fresh quantum state, full of rich, overlapping details. But as time passes, that memory is constantly bombarded by the environmental noise of your life, new experiences, distractions, and even other memories. Each interaction subtly alters the original imprint, causing it to lose its coherence and sharpness. The memory does not vanish, but it decoheres, settling from a vibrant superposition of possibilities into a single, fuzzy, classical story. This is why two people can remember the same event so differently, their respective memory states having decohered along unique paths shaped by their personal environments and subsequent experiences. This quantum metaphor offers a profound perspective on the nature of our own minds. We are not just forgetting, we are undergoing a constant, gentle collapse from the quantum potential of a moment into the settled history of a life lived. What does it mean that the very process that makes the world feel solid and predictable is also the same force that softly erases our yesterdays? The confirmation of Einstein's grandest prediction arrived on a whisper, a ripple in spacetime 1 billion times smaller than an atom. Detecting such an impossibly faint signal required listening past the fundamental noise of the universe itself, a task achieved only by squeezing the void. At the heart of the LIGO Observatory, lasers race down 4-kilometer-long vacuum tubes, their beams perfectly aligned to sense the subtle stretching of space caused by a passing gravitational wave. Yet, according to the Heisenberg uncertainty principle, there is a fundamental limit to how precisely you can measure the phase and amplitude of a light beam, a constant quantum jitter known as shot noise. This quantum fuzz would have drowned out the faint cosmic signal forever, if not for a remarkable quantum technology called squeezed light. By carefully engineering the quantum state of the laser light itself, scientists can redistribute this inherent uncertainty, squeezing the noise in one property at the expense of increasing it in another. It is like quieting a persistent hum in one key frequency so you can finally hear the symphony playing just beneath it. This manipulation of quantum noise, this deliberate bending of Heisenberg's rule, allowed LIGO to achieve a sensitivity once thought impossible. Our first direct observation of colliding black holes, a monumental validation of general relativity, was delivered to us on a beam of quantum-squeezed light. The largest events in the cosmos, the collisions that shake the fabric of reality, are now revealed to us only because we learn to quiet the quantum whisper at the heart of nothingness. This marks a profound turning point, where our exploration of the universe is no longer just an act of astronomy, but one of quantum optical engineering, a silent partnership with the fundamental rules of light to hear the secrets of the dark. Even the most intuitive rules of cause and effect begin to fray at the quantum scale. We are taught that a force must act directly on an object to change its path, but the quantum world operates on a subtler logic. Consider an electron traveling through a region of space where both the electric and magnetic fields are precisely zero. By all classical reasoning, it should continue on its way completely unaffected, a lone traveler in an empty room. Yet, in a stunning defiance of expectation, its quantum wave function can be shifted, its interference pattern altered, as if it were pushed by an invisible hand. This is the Aharonov-Bohm effect, and its secret lies not in the fields of force we can measure, but in the underlying electromagnetic potentials from which those fields are derived. The electron is not responding to a local push or pull because there is none. Instead, it is sensitive to the global landscape of this potential, a hidden topography of influence that exists even in the complete absence of force. It is as if a ship's compass were deflected not by any local magnet, but by the memory of a magnetic field that once filled the harbor. This effect forces a profound revision of our physical intuition. The electromagnetic potential is not just a convenient mathematical tool for calculating fields. It is a real, physical entity in its own right, capable of dictating the fate of a particle from a distance. This subtle quantum dance reshapes our most basic notions of locality and influence, suggesting that the universe keeps a deeper set of books than the ones we can directly observe. If an electron can be guided by a ghostly potential in a field-free void, what other invisible landscapes are quietly shaping the reality we perceive? The information that defines a particle, its unique quantum identity, can be sent across the universe without ever physically traveling the distance between. This is quantum teleportation, a process that sounds like science fiction but is now laboratory reality. It is crucial to understand that we are not teleporting the physical particle itself, like a tiny speck of matter being beamed from one place to another. Instead, we are teleporting its precise quantum state, the fragile configuration that makes it unique. The procedure relies entirely on the spooky link of entanglement. Imagine you have two entangled particles, let us call them Alice and Bob. You keep Bob in a secure location while Alice is sent far away. Now you have a third particle, carrying the precious quantum information you want to teleport. You bring this target particle together with Alice and perform a special joint measurement. This measurement instantly entangles the target with Alice, but because Alice was already entangled with Bob, this action has a miraculous consequence. It destroys the original state of the target particle and simultaneously forces Bob, no matter where he is, to instantly take on that exact same quantum identity. The original information is gone from the source, faithfully recreated in the distant particle. This is the foundation for a quantum internet, a network where information security is guaranteed by the laws of physics. Any attempt to eavesdrop on the transmission would break the delicate entanglement, immediately alerting the users that their channel has been compromised. The future of global communication may not be built on streams of light, but on the silent, instantaneous collapse of quantum states, weaving a web of perfectly secure connections across the planet. The solid world you take for granted is a consensus reality, but its origins remain one of physics' deepest enigmas. Why does the fuzzy cloud of quantum possibilities resolve into a single, definite event the moment we look? This is the infamous measurement problem, and it forces us to confront a staggering possibility. Perhaps consciousness itself is the catalyst that completes reality. In the conventional Copenhagen interpretation, the wave function collapses upon measurement by a classical instrument. But where is the line between the quantum and the classical? A single atom is quantum, a Geiger counter is classical, but what about the individual molecules within the counter? This chain of ambiguity leads all the way to the human brain. Pioneering physicists like John von Neumann and Eugene Wigner proposed a radical solution, that the final collapse is caused by the conscious observation of a sentient being. In this view, the universe exists in a haze of potential until a mind perceives it, making consciousness a fundamental force in shaping existence. This is not a mainstream scientific position, but it ignites a firestorm of philosophical debate that bridges the gap between the objective and the subjective. Are we merely passive witnesses to a universe unfolding on its own, or are we active participants, essential for bringing it into full being? Every time you glance at a clock and see a specific time, you are not just reading a value, you might be finalizing it, collapsing a superposition of all possible moments into the one you call now. This idea places our inner world of awareness at the very heart of cosmic law, suggesting that the quest to understand the atom is inseparable from the quest to understand ourselves. The silent guardians of our national borders are no longer just soldiers and satellites, but the immutable laws of quantum physics. In the world of state secrets and diplomatic cables, the ultimate defense against digital espionage is a technology that turns eavesdropping into an impossibility. This is the 30th connection, where quantum cryptography has become the gold standard for protecting the world's most sensitive communications. The core principle is both simple and unbreakable. When a message is encoded into the quantum states of individual photons, any attempt to intercept it is not just a risk, it is a guaranteed event. An eavesdropper cannot passively read a quantum signal. They must interact with it to measure it, and that very interaction will inevitably alter the fragile quantum state of the photon. This disturbance is immediately apparent to the legitimate sender and receiver, who can see the statistical anomalies in their transmission. They know with absolute certainty that their channel has been compromised, and they simply discard that batch of data. It is a security system that does not just make interception difficult, it makes it fundamentally detectable. This relies on two profound quantum laws. First, the principle of indeterminacy, which means the eavesdropper cannot perfectly copy or clone the unknown quantum state due to the no-cloning theorem. They cannot make a perfect replica to read while letting the original pass undisturbed. Second, the act of observation is an irreversible physical interaction that always leaves a mark. The highest levels of government and military strategy, the movements of fleets and the words of treaties, are now entrusted to this quantum seal. A single photon, carrying a fragment of a cipher, becomes a more formidable sentry than any firewall, because its integrity is protected by the fabric of reality itself. Our collective safety is quietly underwritten by the same spooky rules that govern particles in a lab. A silent quantum pact ensuring that some secrets remain truly secret. Our understanding of particles, from orderly bosons to exclusive fermions, is fundamentally rewritten in two dimensions. When a flat sheet of electrons is trapped at near absolute zero and subjected to an immense magnetic field, a new chapter of quantum behavior unfolds, the fractional quantum Hall effect. Here, the electrons collectively organize into an intricate quantum fluid, And from this fluid emerge excitations that are neither Fermion nor Boson. These are anyons, a third category of particle whose existence was once purely theoretical. Their magic lies in their statistics, the quantum memory of their paths. When two identical fermions are swapped, their quantum wave picks up a phase shift of 180 degrees, a negative sign. Swap two bosons and the wave remains unchanged. But when you slowly move one enyon around another in the flatland of a two-dimensional system, their collective wave function remembers the braiding, the intricate dance of their paths. This topological memory makes anyons far more than a laboratory curiosity. They are the building blocks for a new kind of computer. In a topological quantum computer, information would be encoded not in fragile quantum bits, but in the braiding patterns of anyons. The very act of swapping these particles around one another would perform a calculation. Because the information is stored globally in the system's topology, not locally in a single particle, it becomes incredibly robust against the decohering noise of the environment. A single flaw or perturbation cannot easily destroy the intricate braid. This means the quest to understand matter under the most extreme conditions has revealed a path to fault-tolerant quantum computation, a system where the universe's own geometric rules protect the integrity of our data. The future of computing may not be written in silicon, but woven into the ghostly trails of quasi-particles that exist only when electrons are confined to a plane and pushed to their quantum limit. The solid ground of cause and effect begins to dissolve in the face of the quantum eraser. A particle is sent on its way, and based on how we choose to measure it later, we can seemingly rewrite the history of its journey. This is the delayed choice quantum eraser experiment, and its implications are as profound as they are strange. In one version of this test, a photon is split, its two possible paths heading toward a pair of detectors. Common sense dictates that the photon must have taken one path or the other from the very beginning. Yet, by cleverly arranging a final measurement after the photon has already finished its trip, experimenters can choose whether the photon behaved like a single particle on a definite path or like a spread-out wave that took both routes simultaneously. The present choice of measurement appears to reach back in time and dictate what the particle did in the past. This is not literal time travel, but it profoundly challenges our linear understanding of causality, the unbreakable rule that the cause must always come before the effect. Here, the effect, our choice of how to look, seems to retroactively determine the cause, the particle's prior behavior. This quantum retrocausality finds a deep echo in the human experience of memory. A present decision, a new perspective, can entirely reshape the narrative of your past. A childhood failure, once a source of shame, can be reinterpreted through the lens of your current success as a necessary lesson that forged your resilience. The past itself did not change, but its meaning and its causal power in your life are altered by your present observation. The quantum world and the world of human consciousness both whisper the same unsettling truth: that time may not be a simple, one-way street, but a far more intricate tapestry where the future and the past are in a constant, delicate dialogue. That solid reality you trust is a story told by the environment itself. Quantum Darwinism offers a compelling answer to the measurement problem, suggesting the universe has its own way of voting on what becomes real. In this view, the quantum world is still a sea of probabilities, but some states are far more resilient than others. When a quantum system interacts with its environment, whether through air molecules, photons of light, or even distant gravitational fields, these robust states are the ones that get copied and broadcasted most effectively. Think of a single water molecule in the ocean. Its quantum state is fragile and private, but the ocean's overall temperature is a classical property that has been redundantly imprinted onto countless other molecules. A piece of data copied so many times that it becomes an objective fact accessible to anyone who dips a thermometer into the water. This is the essence of quantum Darwinism. The environment acts as a witness, constantly measuring the system and selectively amplifying only the most stable, fittest quantum states. These are the states we all agree upon, the pointer states that define our shared classical world. The rock is hard because its molecular structure has been redundantly imprinted on the light bouncing off it, and the air touching it, creating a consensus so overwhelming that your brain receives the same objective data as everyone else. This process is strikingly similar to how a dominant narrative emerges in our social media feeds. A single event holds countless potential interpretations, a quantum cloud of possible stories. But the ones that are most shareable, most resonant, or most emotionally charged are the ones that get copied, liked, and retweeted into a perceived objective truth. We all converge on the same headline not because it is the only version of events, but because it is the one the digital environment has selected for and amplified most vigorously. Our shared reality, from the chair you are sitting on to the news you discuss with friends, may simply be the quantum state that won the popularity contest. Its story told so many times by the world around us that we all hear the same version. That red dot dancing across a presentation screen is a tiny, controlled quantum eruption. The common laser pointer, a device of pure convenience, is a pocket-sized marvel of cavity quantum electrodynamics, a field exploring how light and matter interact within a confined space. Inside its plastic shell, a small crystal or diode acts as the quantum engine. Energy is pumped into this material, exciting its atoms and pushing their electrons into higher energy levels. These excited electrons are unstable, and they naturally want to fall back down, releasing their excess energy as photons of light. In an ordinary light source, like a light bulb, this happens randomly, creating a chaotic jumble of light waves out of sync with one another. But inside the laser's optical cavity, a space bounded by mirrors at each end, something extraordinary occurs. One photon, emitted spontaneously, can trigger a chain reaction. As it bounces back and forth between the mirrors, it stimulates other excited atoms to release their photons in perfect lockstep. This process, called stimulated emission, forces the new photons to match the original in every way: same frequency, same direction, and critically, same phase. The light waves march together in a perfectly coherent, single-colored beam. One mirror is partially transparent, allowing this amplified, unified light to escape as the laser's pinpoint dot. We have not just built a tool, we have engineered a quantum process, creating order from atomic chaos by confining light and forcing it to cooperate. This mastery over stimulated emission means we are no longer mere observers of quantum phenomena. We are conductors of a light orchestra, directing the precise quantum leaps of countless atoms to produce a beam so straight and pure, it can measure the distance to the moon. That humble pointer on your desk is a testament to our ability to command the quantum world, bending its probabilistic nature to our will for a purpose as simple as highlighting a bullet point. You are held to the ground by an invisible, cosmic molasses, the very substance of your body, the weight you feel when you pick up a book, the resistance you meet when you push a door. All of this tangibility has a startlingly ethereal origin. The discovery of the Higgs boson at the Large Hadron Collider was not just the discovery of another particle. It was the confirmation of a cosmic mechanism, the Higgs mechanism, that answers a profound question. Why does anything have mass at all? The universe is filled with an invisible quantum field, the Higgs field, which pervades all of space. Think of it not as empty nothingness, but as a vast, still ocean. As fundamental particles like electrons and quarks move through this field, they interact with it. Some particles, like photons, which are particles of light, slip through completely unaffected. They are the cosmic kayakers, gliding without resistance, and that is why light has no mass and travels at the ultimate speed limit. But other particles, like quarks, interact strongly with this field. They are like a person wading through deep water, Their movement slowed, their progress resisted. This resistance is what we experience as mass. The Higgs boson itself is a ripple in this field, a fleeting confirmation of its existence. This means the solidity of your desk, the heft of your own hand, is not an intrinsic property of the matter itself. It is a gift from the universe, an emergent property born from a particle's ongoing conversation with an invisible quantum ocean. The world you can touch and feel is, in its most fundamental essence, a persistent illusion crafted by a field of pure potential. How many other tangible truths of our existence are merely the surface ripples of a deeper, hidden quantum sea? The most efficient route for your next delivery was likely discovered by a machine that thinks in quantum probabilities. Behind the scenes of our global economy, a new kind of computer is tackling problems that would stump even the most powerful supercomputers for centuries. Companies like D-Wave are building quantum annealers, specialized machines designed not for general computation, but for solving fiendishly complex optimization puzzles. These are the problems that underpin our modern world, from scheduling thousands of airline flights to minimize delays, to modeling financial risk in volatile markets, or finding the most efficient path for a fleet of delivery trucks through a congested city. A classical computer must painstakingly check each possible route one by one, a process that becomes impossibly slow as the variables multiply. A quantum annealer approaches the problem differently, by framing it as a vast, multi-dimensional energy landscape. Every possible solution is a point in this landscape, with the worst solutions represented as high peaks, and the best solution as the absolute lowest valley. The machine starts by placing a quantum system into a simple, high-energy state, a superposition of all possible answers at once. Then, it slowly guides the system, allowing it to explore this complex terrain not by climbing over every single mountain, but by using quantum tunneling to pass straight through them. It is as if the computer gives the problem a map of all the hills and valleys, and then lets a quantum ghost simply appear in the deepest basin, having bypassed all the obstacles in between. This is not raw processing power. It is a fundamentally different kind of intelligence, one that leverages the inherent fuzziness of the quantum world to find optimal paths through a maze of possibilities. The future efficiency of our supply chains, our financial systems, and our energy grids may soon depend on our ability to harness these quantum shortcuts, turning the most daunting logistical nightmares into elegantly solved equations. That lingering sense of what if, the ghost of a path you did not take, might be more than just a feeling. It could be a whisper from a parallel reality. The controversial many worlds interpretation of quantum mechanics proposes that every time a quantum system faces a probability, the universe does not choose. Instead, it splits, with every possible outcome realized in a newly branched world. When you decided to take that job offer in a new city, another version of you, in a universe just as real, chose to stay. That wave function never collapsed, it simply decohered, and the two possibilities drifted apart into separate, non-communicating timelines. This idea transforms regret from a monologue into a cosmic dialogue. The career you did not pursue, the person you did not speak to, the risk you did not take, all of these are not lost. In the vast, branching tree of reality, they are all happening. This can be a profound comfort, a balm for the ache of missed opportunities, suggesting that no potential is ever truly wasted. Yet, it can also feel terrifying, an infinite multiplication of responsibility where every minor choice spawns countless alternate selves. The weight of your life is not that you chose one path, but that you are aware of only one path, while an infinite ensemble of you experiences all the others. This quantum interpretation reframes our very existence. We are not walking a single, predetermined line, but are instead navigating an ever-forking river, with each decision point creating new streams of consciousness. The nostalgia we feel for a past that never was might be a faint, quantum resonance with a self who is living it. Are we solitary travelers, or are we the focal point of an infinite tapestry of lived experience? Each thread a different answer to the question, what if? The familiar drag of your shoes on pavement, the heat from rubbing your hands together, these are the classical signatures of friction. Yet at the invisible frontier of nanotechnology, this force transforms into something far stranger. When two surfaces are brought to within nanometers of each other, but never actually touch, a subtle resistance can still emerge. This is quantum friction, a drag force born not from physical contact, but from the restless dance of quantum fluctuations. Even in a perfect vacuum, the electromagnetic fields between the surfaces are never truly still. Virtual particles wink in and out of existence, creating a fluctuating force that can siphon energy away from a moving object. It is as if the void itself has a kind of viscosity, a whisper-thin molasses that only reveals itself at the smallest scales. For the engineers designing nanomachines, molecular motors, and atomically precise devices, this quantum drag is a fundamental design constraint. A microscopic gear, spinning in the void, could gradually slow down not because of any mechanical flaw, but because of the gentle, insistent pressure of the quantum vacuum itself. This means that the ultimate limit to miniaturization, the final barrier to building ever smaller machines, may not be our skill at carving atoms, but the inherent stickiness of empty space. The very void, it seems, pushes back. This profound connection forces us to reconsider the nature of motion itself, suggesting that smooth, frictionless travel is a quantum impossibility, a dream forever haunted by the ghostly static of nothingness. The rigid predictability of a ticking clock defined our universe for centuries. Isaac Newton bequeathed us a cosmos of absolute certainty, a majestic clockwork where every action spawned an equal and opposite reaction, and the future was as predetermined as the past. If you knew the precise position and velocity of every particle, you could, in theory, calculate the entire unfolding of history. This was a comforting, comprehensible world, built on the solid ground of cause and effect. Then, at the very end of the 19th century, a tiny crack appeared in this elegant facade. Physicists were studying the light emitted by hot objects, a problem known as blackbody radiation, and the classical equations failed catastrophically. They predicted an ultraviolet catastrophe, an infinite amount of energy radiating at high frequencies, which was clearly absurd. Into this crisis stepped Max Planck. In a move of sheer desperation, he proposed that energy was not emitted in a smooth, continuous wave, but in discrete, indivisible packets he called quanta. This was a mathematical trick, a Hail Mary to make the equations work, and Planck himself was deeply unsettled by its physical implications. He had, without realizing it, struck the first blow against the classical edifice. The next great shock came from a young patent clerk, Albert Einstein. He took Planck's quantum idea seriously, applying it to another stubborn puzzle, the photoelectric effect. Shining light on a metal surface could knock electrons loose, but the energy of those electrons depended not on the light's intensity, but strangely on its color. Einstein proposed that light itself was quantized, made of particle-like packets we now call photons. This was heresy. Light was a wave, how could it also be a particle? Yet the math worked perfectly, earning Einstein his Nobel Prize and shattering the wave-particle duality into physics. The foundations were trembling, and a young Dane named Niels Bohr would bring the quantum revolution to the atom itself. He proposed a radical new model where electrons could only orbit the nucleus in specific, allowed energy levels, making quantum jumps between them. This explained the sharp lines in atomic spectra, but it made no classical sense. Why were only certain orbits permitted? The answer was emerging from the mind of Louis de Broglie, who suggested that if waves could act like particles, then particles like electrons must also have wave-like properties. This was confirmed when electrons were diffracted just like light waves. The universe was not just a clock, it was also an orchestra. The final, decisive break with common sense came with the formulation of quantum mechanics by Heisenberg and Schrödinger. Heisenberg's matrix mechanics introduced his famous uncertainty principle, placing a fundamental limit on knowledge. You could know where a particle was or where it was going, but never both with perfect precision. Schrödinger, meanwhile, gave us the wave function, a mathematical expression that described a particle not as a tiny ball, but as a cloud of probability. His famous cat, both alive and dead in its box, was a thought experiment designed to highlight the sheer absurdity of applying this quantum weirdness to the everyday world. Bohr and Einstein then clashed in a legendary debate over the meaning of it all. Einstein, refusing to believe God played dice with the universe, devised clever thought experiments to prove quantum mechanics was incomplete, only to have Bohr repeatedly defend the theory's bizarre, probabilistic core. This historical journey from a universe of certainty to a realm of probability is not just academic trivia. It is the essential backdrop that makes every one of these 38 connections so astonishing. We had to abandon everything we thought we knew about reality to discover a truth far stranger and more wonderful. A truth that is woven into the fabric of your morning coffee, your smartphone, and your very thoughts. This quantum thread, connecting your morning coffee to the fate of galaxies, reveals a universe far more unified than the old categories suggest. We have spent over a century drawing a firm line between the quantum and the classical, treating the world of atoms as a bizarre separate kingdom with rules that do not apply to our own. But these 38 connections dismantle that wall entirely. The quantum world is not a distant, microscopic realm. It is the foundation, the hidden architecture upon which your daily life is constructed. It is the operating system running quietly in the background of everything you see, touch, and experience. Your technology, your biology, your social instincts, and even your language are all expressions of this deeper, probabilistic reality. The green of a leaf, the security of a message, the solidity of a wall, all emerge from quantum processes. This is not a collection of isolated curiosities, but a coherent tapestry. The same principle of superposition that governs an electron is reflected in your moment of indecision. The same entanglement that secures data mirrors the deep bonds of human relationship. The universe is speaking one language, from the smallest scale to the largest, and we are finally beginning to understand its grammar. This demands a fundamental shift in perspective, from seeing science as a set of compartmentalized disciplines to viewing existence as a single, integrated whole. Biology, psychology, technology, and cosmology are not separate stories. They are different chapters of the same epic, all written with the same quantum ink. The next time you feel the sun on your skin or hesitate before a choice, you are not just living your life. You are participating in a grand cosmic dance where every action, every observation, and every connection is a note in a symphony composed by the rules of the very small. We have journeyed together through 38 astonishing connections, from the phone in your pocket to the thoughts in your head. This exploration reveals a universe not of separate parts, but of a deeply woven tapestry, where the same strange rules govern the sun's core and your morning indecision. The quantum world is not a distant laboratory abstraction. It is the hidden architect of your reality, the quiet hum inside every ordinary moment. Let this new perspective reframe your day, transforming the mundane into the miraculous. Notice the quantum leap in a sudden idea. Feel the observer effect when you catch someone's eye, and recognize the entanglement in a shared glance. Your world is alive with hidden connections, waiting only for your attention to be revealed. If this journey through the quantum fabric of life intrigued you, share your most surprising connection in the comments below. and subscribe for more explorations into the mysteries of our universe.